Good morning. We're here today to talk about improving manufacturing problem solving. As a quick procedural note, if you have questions during the presentation, please enter them into the Q&A. I will get to them at the end of the webinar. Thanks. The agenda today is straightforward. We will take a look at current problem solving practices in manufacturing and how they can be improved using Industry 4.0 solutions. What is the problem solving process? The graphic on the right side is from Jeffrey Liker's seminal book, The Toyota Way. It walks through Toyota's practical problem solving process. It begins with the general identification of an issue within the plant. The next several steps work to clarify the nature of the problem itself, and then perform root cause analysis to identify the reasons why the problem is happening. At this point, solutions are identified and put into place and then evaluated and standardized. An example would be where people feel there is too much downtime on a particular machine. Solving the problem would then be clarifying the nature of the downtime, measuring the amount of downtime that is being experienced, and locating the point of cause in the machine that is failing. The team would then perform a 5 why root cause analysis and determine the countermeasures to eliminate or at least mitigate the root causes of failure. They would then evaluate the performance after the fixes to see if they had the desired impact. And at that point, the fixes would become part of the standard work for that machine and potentially be replicated to other areas of the plant where applicable. Well, as we can see, the practical problem solving approach is not the only one in manufacturing. There are quite a few standard problem solving processes within manufacturing. There are many commonalities between the different methods, and they largely contain the same steps, just grouped and organized a bit differently. One question I often get is, which is the best or right technique? While there are some differences between the different systems, they really have more in common than they have difference. My recommendation is that if the team has already been trained on one technique and is familiar with it, then that's the best one to use. At that point, it really becomes a question of how to improve the execution of the process and how to support the personnel as they proceed through each step. Another question I sometimes get is to differentiate between the small continuous improvement steps and larger improvement events. In his excellent book, 2-Minute Lean, Paul Akers makes a compelling case for an emphasis on the small improvements that only take minimal resources and minimal time to make those incremental repeated steps in performance that add up over time. And while the primary focus for today's presentation is with the larger issues that arise in manufacturing, the concepts we'll cover about smart manufacturing solutions can apply to these quick changes too. In this case, the focus is on giving operators what they need to implement small improvements at their stations. Context about the performance at the station and its impact on the overall flow, summary and detailed information about the problems in a way that's quick and easy to consume, and then measurement and feedback on whether the change that they have made was successful. Broadly, everything we'll cover for the larger projects applies here as well. It's simply more focused and formatted for small continuous improvements. Next, we'll look at the steps in the typical manufacturing problem-solving process and how those can be impacted by smart solutions. So the problem-solving process that we'll walk through for the rest of the webinar, I've simply combined the steps from the different practices into one list. It's not meant to be a recommendation for yet another workflow, but just to show how smart manufacturing solutions can support all of the steps in each of the practices. As we walk through the steps on the following slides, we'll see how they can be improved through historical performance information that captures production rates, uptime and downtime information, quality data, and much more. Detailed process process data showing pressures, temperatures, vibration information, PLC tag data, etc. Through contextual information for each one of the different events, who was running the process, what was being manufactured, what was the time of day of week, and much more. Augmented intelligence capabilities through artificial intelligence and machine learning. Well-designed workflows that help users through the problem-solving steps. Structured communication platforms that keep the team on the same page and facilitates group productivity. And then advanced data visualizations to help make the information easy to understand for all of the participants. So step one is the initial identification of problems. And as is said, the first step is admitting that you have a problem. On any manufacturing floor I've ever been to, there's really never been a lack of issues to be addressed. There are always problems to fix, processes to improve, and so forth. What smart factory solutions help with here is to understand the scale of the different problems. The historical performance information shows exactly how big each problem is, how they are trending, and much more. This helps to determine which should be the highest priority issues to work on. The systems allow the creation and tracking of a project funnel for the facility that looks at these different problems and prioritizes them. Instead of simply chasing the last major event or the squeaky wheel, the team can prioritize the most impactful work that can be done. Step two is to form the team. Once it's decided which problem is going to be addressed, a team has to be assembled. While the smart factory systems won't help with forming the team itself, they are fantastic for facilitating teamwork and communication. Well-designed workflows help users through the problem-solving steps, showing the relevant information at each step, tracking inputs from multiple users, and consolidating information in a single platform. Most projects today have information spread through multiple systems and even more in multiple Excel spreadsheets that have access and version control issues, and all of that can be eliminated. It provides structured communication platforms that keep the team on the same page and facilitate group productivity. In addition, modern platforms facilitate communication by integrating tools like Microsoft Teams or Slack. Instead of having communication happening across multiple emails and spreadsheets, communication can be facilitated right into the workflow and analysis platform. Step three is to clarify and describe the problem. And one of the key benefits to these systems is the contextual information captured for each one of these different events: who was running the process, what was being manufactured, et cetera. And one of the most basic methods for finding the cause of problems is to ask the 5 different W questions and the 1 H. I think I learned that all the way back in elementary school. When you want to find something out, ask those basic questions to get to the bottom of things. And this method can be very beneficial if it's done correctly. For example, if you're preparing to create charts of possible causes or perform a statistical analysis, or if you're simply trying to clarify and describe a problem, this method can help you identify different potential causal factors. It can also help you just describe the different aspects of a particular failure as well. And it can also be used as a brainstorming tool to be fairly comprehensive in your approach. However, it does tend to lead to somewhat simplistic analysis, as it doesn't try to get the practitioner to drill down any further into or beyond those top level causes. So, it's not a true cause analysis, but it does help you really describe the whole problem and be very clear about what the problem really is. And so when performing the analysis, Industry 4.0 provides capabilities that automatically capture accurate information about each one of these potential cause categories. Keeping with the example about first pass yield from earlier, information can be captured directly from the testing machines on how the part failed the test. The system can know who is logged into the stations by knowing what machines were used for which parts. The system can know where the problem occurred. They can also know when the defect happened. And by tracking detailed process variables as the part was processed, the system can track what happened during production. And so as we collect all of that information automatically and on a repeated basis, we can accumulate this information to show a really thorough and good description of what's really happening with the problem. A quick note on integrating artificial intelligence or machine learning systems into the process. On the previous page, we talked about the benefits of the contextual information, allowing the team to better clarify and describe the problem. It's also possible to augment the analysis with AI capabilities. Classifier systems can automatically group similar events across a range of different dimensions, and other types of AI can perform other tasks automatically as well. That means that the team doesn't have to do all the heavy lifting with the analysis. The software can help them out with that process. I'm not going to go more in depth on this today, but I've done other webinars on that subject where if you reach out to me, I can get you links to those events as well. Step 4 is containing the problem. And by understanding what are the different things that are contributing to the problem and having that clear definition in place, we're now in a position to implement a short-term fix. While we shouldn't be satisfied with putting a Band-Aid on the problem, so to speak, this can contain quality or safety issues while a permanent fix is sought. And having that good analysis in place prior to this point will really help to determine the proper containment measure to implement. So step 5 is root cause analysis, and we'll spend a little bit on this one. There are many different frameworks for performing root cause analysis. In other webinars, I've gone through the details on each of these different methods, and today I'll give more of an overview on how each can be impacted, as well as drilling deeper into a few of the different methods discussed here. So the 5W and 1H was discussed earlier in terms of really properly clarifying and describing the problem. And sometimes it's sufficient to get to the root causes for performance. For example, if it's somebody simply not adhering to standard work and setting up the machine improperly, if you see that, then you can pretty much immediately solve that problem once you've identified that issue. Graphical evaluation. So in this method, data about the process is put into graphical form where the users can evaluate it visually. And at Visual Decisions, we're really big fans of this type of analysis. Smart manufacturing systems are fantastic for this type of problem solving. Because they're so data rich, most of the information you'd like to know about the process can be charted and shared for analysis. And FMEA. In another webinar, I've described how to create an evergreen FMEA, or failure mode and effect analysis, that is continually updated with information from the shop floor. Based on the symptoms observed from the shop floor, this tool can be used to see if there are known causes for failure that you should investigate right away. We'll look at the rest of the methods on the following slides. 5Y is easily the most common type of root cause analysis done in lean manufacturing environments. In this method, we keep asking why until we get down to the root cause of the problem. In the example shown, our problem is that the customer's refusing to pay for the leaflets we printed for them. Our top level reason is that the delivery was late, so the customer could not use the leaflets. Instead of settling for that answer, though, we can continue to ask why. In this case, the next question was, why is the delivery late? Eventually, we reached the root cause of the problem, that we ran out of ink and couldn't order additional supplies in time. And at this point, we've reached a cause that we can take action on. So we put countermeasure in place to find a backup ink supplier we can use when in emergencies, so that we can continue our normal, keep our normal stock minimized, but have a place to go to for periods of surge demand. The biggest trap I've encountered with the 5Y analysis is that people only ask why one time at each level. In the example given, we really only had to answer why once to each question. In reality, though, there's usually more than a single cause for each question. So instead of ending up with a straight line, you should end up with something that looks like a tree. And the other key problem that I've seen is that this is usually not done with data. It's usually done by gathering people into a conference room and asking people to go through the process anecdotally. And when you go through the process anecdotally, you can end up going down the wrong path. So 5 why analysis can be greatly facilitated by having data at each one of those different levels. In addition to the traditional brainstorming, the team can investigate the data to see what it shows as each question is asked. Next, we'll look at the Fishbone or Ishikawa diagram. In this method, you show the problem or effect to the right side of the diagram, shown in the triangle on the right side. And then you try to determine all of the different contributing factors to the problem. It's typical, but not required, that the first branches in the analysis are man, machine, material, method, management, and environment. Then you ask what it is in each one of those different areas that might contribute to the issue. And you continue asking why until all of those different root causes are reached. Essentially, it's a 5 why with a structure that encourages asking why more than one time at each level. Again, though, this is usually done in a highly manual fashion that's disconnected from the process. And another weakness is that while the diagram gives an idea of the different contributing causes, it doesn't really show how much those causes contribute to the problem. When data collection is performed with this, it's usually done manually after the initial analysis has been completed. And one way that this is done is either to give the operators tick sheets or to have somebody go out and watch the process. And when you're watching the process, the problem is that you have something called the Hawthorne effect. People behave differently when they're being watched. Think of how drivers slow down when there's a policeman on the side of the road. This leads to the problem of bias in the data. The data that gets collected does not accurately reflect how the process normally operates. With Industry 4.0 solutions, we collect data all the time. This allows us to create a Pareto diagram of how much each one of these causes is contributing to the issue. Then we can begin the Kaizen event or improvement event with a very strong data set on all of the different causes and how much each of those causes contribute to the problem and what's most important to address first. Finally, we close out this section with a brief discussion of the gold standard of data-based root cause analysis. Some forms of statistical analysis that apply here are analysis of variance or ANOVAs, design of experiments or DOEs, linear and multiple regression, t-tests, chi-square tests. All of these methods are at the heart of Six Sigma analysis. It's beyond the scope of this particular webinar to dive deeply into each one of these different statistical methods. I do want to cover a few important points though. These generally represent tested hypotheses where the hypothesis represents a potential cause for the problem. In many cases, the preceding methods can be used to identify the candidate causal factors for the problem, while these methods can be used to confirm whether those factors are truly correlated or causal to the outcome. Obviously, these methods are very heavily dependent on the data. The more data, the better. The richer and more contextualized that data can be, the better these methods will work. And another key advantage is that you have this rich historical data. So essentially you can perform a DOE on the history rather than collecting new data to perform that experiment. It doesn't always work out that way. You have to have the right data collected in advance, but if you do have that right data collected in advance, you can iterate through these cycles of analysis very quickly. Step 6 is to create solutions. Another big impact of Industry 4.0 is to broaden the solution space. For many problems in manufacturing, the fix will be some alteration to the physical equipment involved. Going back to that Fishbone diagram, those fixes primarily relate to the machine branch of that Ishikawa diagram. However, when the problem is related to man, material, method, management, or environment, the fix is often process or system-based. Just as a quick example, many times the problem can be traced back to a lack of standard work or a lack of adherence to the standard work. And in all of those cases, smart factory systems can be an integral part of the solution. In many quality-related problem-solving efforts, technology can be a key part of error proofing, automated inspection, and other solutions. And for these solutions, technologies of Industry 4.0 can provide tremendous benefits. There are many additional ways that smart manufacturing solutions can help create solutions as well. The usual way to go about creating solutions is to look at a number of different alternatives. You want to brainstorm and utilize cross-functional teams. You can incorporate vendors, partners, customers where beneficial. This may mean getting input from people at remote locations. And these days, it can help to have augmented reality capabilities to get remote visibility into the process for those external experts. Another key capability is being able to track what has been done before and utilize those best practices. Being able to see if this machine has had the same type of failure before, what did we do then? Was it successful? How long did the fix last? Why did it break again? Was there a fix done on a similar piece of equipment that worked better or lasted longer? For maintenance repairs, this information might be in a typical maintenance management system. However, there has to be a way to capture changes like process fix, additional training, changes in standard work, et cetera, that won't be in that MMS. And there can be implementing these different solutions means that there can be one central place to look for different solutions that have been tried in the past. Another trap to avoid is that that's just the way that the process works. As an example, I worked with a customer to improve a shampoo bottle filling line. In the data, I noticed that there were a lot of short stops being attributed to the filler. When I drilled into the data, I found that the overhead bottle feeder to the filler was jamming. And the current solution to the problem was that the filler would stop, and wherever the operator was on the line, they wouldn't know that the filler stopped until whatever part of the line they were standing at stopped as well. And that could take a couple of minutes. And once the operator saw that the line had stopped, he kind of walked backwards in the process until he saw where it stopped. Usually it was the filler. And then if that overhead feed was jammed, he'd grab a broomstick and he'd poke at it until the feed resumed. And then the filler would start up and feed the rest of the line again. And when I discussed that with the team, they were really a bit defensive about it. They said it only took a few seconds to fix the jam when it happened, and that's just the way the line worked. So I led them through the data to show the real impact of the problem. That jam was sometimes occurring 20 times a shift. It's true that the operator could clear the jam in a few seconds. They really got very skilled with that broomstick, but it was a long line with a single operator. The filler could be stopped for a few minutes before the operator would see it and get to the jam to clear it. That silly little jam was actually the biggest source of downtime for the process. So we gathered the process engineer, the operator, the supervisor, the maintenance team to the line to brainstorm different solutions. And in the end, we put in two key fixes. The first was to fix the alignment of a joint in the feed that was causing the bottles to jam in the first place. And the other was an andon light to let the operator know right away when the filler, which was the gating process for the line, stopped for any reason. And that improved the OEE and the overall performance of that line dramatically. Step 7 is testing the chosen solution or solutions. If you're implementing technology as part of your solution, you want to make sure that you adapt the process and provide adequate training to your people for that process change. Simulation provides another key capability here from an Industry 4.0 perspective. If the potential solution is something that requires capital investment, simulating the solution in advance of making the investment can provide evidence that the solution will actually have the desired impact. A large portion of what we do at Visual Decisions is implementing IIoT or Industrial Internet of Things solutions with our customers. These platforms tend to have tremendous flexibility to address common and uncommon issues in manufacturing. They tend to have some development time associated with them, and a big recommendation is to utilize agile approaches for the development of the solutions. Agile was based in part on the Kaizen philosophy of continual stepwise improvements. And implementing these solutions in this manner really helps to align with the philosophy in manufacturing of continuous improvement, and putting a system in place that doesn't lock in the process to one particular format. Another technology that should be noted here for testing is augmented and virtual reality. Not only can these technologies be part of a solution to many manufacturing issues, but they can also be used to test out a wide variety of other solutions. So they can be used to give insight on how workers may interact with those potential solutions before making heavy capital investments to put them in place. Step 8 is to measure and analyze the results. Much of this webinar has been about utilizing data effectively to identify and analyze issues. And this is yet another place within the problem-solving process that acquiring and analyzing data is crucial. All of these topics touched on earlier apply here as well. In particular, having a system to collect the data 24/7 in an unbiased fashion is critical. Because of bias and inaccuracy inherent in manually collected data, measuring the success of the solution in that fashion will lead to poor results. In addition, it's usually people that have a vested interest in the solution that would be collecting the data, and that makes the solution even more likely to produce biased results. The final step is standardizing the solution. In the previous step, I touched on the dangers of systems becoming monuments in the future. However, here I will mention that one of the potential benefits of software is to standardize the solution. By having a common interface in the software across shifts, machines, or even plants, the software can help systematize the solution across the company. These systems can also be used to document standard work and share that standard work among the operators. In addition, deviations to the standard work can be tracked and used as learning opportunities with the staff. I really can't emphasize enough the key role of standard work here. When we think about standard work in manufacturing, the first thing that pops into mind is getting all the operators to work with the equipment in the same way every time. And that's absolutely part of the solution to many problems. But we also have to think about the leader's standard work. Setting the culture and making a solution part of the process means having the team leaders, supervisors, value stream managers, and executives all be a part of the solution. Some closing thoughts. Data is absolutely critical to identifying the improvement opportunities, identifying causal factors, generating solutions, and more. Caution has to be used to avoid technology monuments. Don't put something in stone that you won't be able to change later. Simulations or situations will change, and you'll want that flexibility going forward. So choose solutions that are easily adapted and improved. And finally, when using some of those flexible solutions, such as IIoT, use agile concepts to implement incremental improvements and test those solutions when reaching the minimal viable product stage of development. That's really it for today's webinar. In the coming weeks, we'll be covering a number of great topics on our webinar Wednesdays. Be sure to go to the Visual Decisions website to register for them today. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve operations since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Thank you for joining us today. If you have questions or would like to talk about how to apply these concepts within your company, please reach out to us. You can give us a call, send us an email, or go to the link at the bottom of the page to set up a meeting directly. Thanks, and see you next week.